Hello, and welcome to the second video for Chapter 2. In this second video, we're going to continue on the idea of the position of celestial bodies around Earth. Now, if you haven't watched the first video, I suggest you do so because that's where I really introduce the ideas about how to think about living on a spherical planet, how to think about the consequences of Earth's rotation around its own axis, things we'll continue to talk about in this video. But in this video, we're going to focus on a few particular movements and, well, angles, configurations. One of those is the tilt of our planet, what's called the axial tilt, which is the reason for the seasons. We will also talk about the moon and how the moon is positioned around Earth, how that causes the phases of the moon due to the relative position of Earth, the moon, and the sun. We'll also talk about eclipses, why they don't happen all the time, but what has to be just right for them to occur. And finally, we will talk about the relative motion of Earth and other nearby planets, in particular Mars, for something called apparent retrograde motion, which is when Earth laps Mars like racers going around a track. But let's get started with the reason for the seasons. Now, other than just asking ourselves what causes the seasons, we also want to ask, how does the orientation of Earth's axis change with time? Because that's the reason for the seasons. Okay? So, true or false? Earth is closer to the sun in summer and further from the sun in winter. What do you think? Is that true or false? And in fact, you don't need to know this as a fact. You can reason out the answer. False. Because when it's summer in America, it's winter in Australia. Right? It has to be false. Because you can't simultaneously have a summer, which is supposedly occurring when we're closest, or that would be one theory, because literally there's winter in another half of the planet. Okay? So that means that we have opposite seasons, so the distance from the sun cannot be the reason for the seasons. All right? Simply put. Okay? If it was, we'd have to have the same season of the entire planet. So every northern hemisphere and southern hemisphere, Australia and America would have to have the same season at the same time instead of opposite seasons. Furthermore, there is a time when Earth is closer. We are sometimes millions of miles, some 8 million miles closer to the sun than other times. That's a significant difference, but it is a small portion because our overall distance from the sun on average is 150 million miles. So we're only varying less than 10%. But that's still, you might think, enough. However, it doesn't actually seem to affect our seasons because the closest time that Earth is to the sun actually occurs during the southern hemisphere summer, which is, of course, the northern hemisphere winter. Well, that would imply that summers are always hotter in the southern hemisphere, but that's not the case. They vary and are quite similar to summers in the northern hemisphere, okay? And we don't have more mild winters in the northern hemisphere either. So it just simply doesn't hold up. It doesn't seem to have a dominant effect that we see in our seasons, okay? So the real reason for the seasons is axial tilt. Okay, but what is axial tilt? What does it mean that our planet's tilted? Relative to what? Well, it's relative to the ecliptic plane. Okay, this is the orbit of Earth around the sun. Okay, it's the average really of all the planets' orbits around the sun, the ecliptic plane. And that plane is inhabited by the planets. In other words, the solar system is disc-shaped, right? Very sparsely populated. All the planets are very far apart, but that's how all the planets rotate, and as viewed from above, counterclockwise direction. But here's the interesting thing. Many of the planets, Earth included, are not exactly aligned with their orbit. They have a rotational axis that's tilted a little bit, sometimes significantly, relative to their orbital axis. Because we could think of the orbital axis as being right here, because the planet orbits around that line pointing straight up out of the ecliptic plane. Think of that as almost like a turntable, and this would be the support sticking right through the middle, okay? So that's the orbital axis. But if we had a rotational axis that was exactly aligned with that, our rotational axis would also have to stick straight up. But look, it doesn't. It's tilted off to the side. We can zoom in here and see that tilt, right? It's pretty significant relative to the straight direction. Okay, that's what we mean by tilt. Many planets have it. Earth definitely has it. Okay, the amount of tilt is 23 and 1/2 degree. So 23 and a half degrees. Okay, if it was 90 degrees, we'd be all the way over on our side and have very different seasons. There is one planet in the solar system that does have a 90-degree tilt. It's Uranus, but its year is so long, the seasons are very muted because they take many Earth years. Each season does. But regardless, we do not have such a extreme axial tilt, but it's still pretty significant. Okay, it results in effects like the North Pole having many days of constant sunlight where the sun never sets, and many days of perpetual darkness where the sun never rises. And likewise in the South Pole, but it was just opposite times of the year. Okay. But the really interesting thing about the axial tilt is the way it stays oriented, because the axial tilt remains fixed to the background of different distant stars. It's not like we're tilted away from the sun and we remain tilted away from the sun. So it's not as if the tilt is relative to the sun, because in that case, when we got to the other side of our orbit 6 months later, we'd still be tilted away from the sun. But we're not, because the tilt of the planet, as I said, is relative to the background. Like I say, the background of distant stars, but just some fixed distant background, something outside of the solar system. So there you see it, right? That means that, for example, the North Pole, which is clearly shown here in both cases, is sometimes tilted away from the sun, okay, like over here, away, and sometimes tilted towards the sun. In fact, half a year later, towards. Okay? That creates seasons. In the extreme case here, thinking about the North Pole, and it's, as I said, long periods of perpetual darkness and constant sunlight. Well, I mean, you can see then that this is right here, when the North Pole is pointing towards the sun, right, during June, right, the month of June, that would be a very bright time in the North Pole. That would be one of the times where there's a midnight sun, the sun never sets. 6 months later, in December, now we have the North Pole pointing away from the sun with the sun never rising up there. In less extreme cases, we could just think about living in North America, all right? Here, you live in North America. During June, you're going to have direct sunlight and very long days. That's going to create hot, long days. That's the summer, okay? Because of the direction and intensity of the sunlight. And then we have 6 months later in winter, check it out, in the Northern Hemisphere, you have indirect sunlight, right, because it's coming in at a steep angle rather than coming in right overhead. Think of it as the fact that in June, the summer would essentially be at the zenith of your local sky. Here, the sun is not that high in the sky in the winter, right? It doesn't get that high in the sky. That less intense light is going to make cooler days, and of course, the days are shorter. So that means that you're in winter, okay? So that tilt, in the way that the tilt is either towards or away from the sun, that's the seasons, okay? That is exactly what creates seasons on Earth, all right? Coming down to the directness of the sunlight, okay? Its intensity and the length of the day. Okay, here's the sun's altitude, all right? Taken somewhere in North America. So it's basically where it is at a certain time of the day on different days of the year. Each dot here would be a few weeks apart. So this time of the year, that's as high as the sun gets. So this is going to be sometime around June, right? About 6 months later, we come down here, and this is going to correspond to December. And this is the sun's zenith in each case, so it's the exact time of day when the sun is highest in the sky. All right, so in December, it just simply doesn't get that high, even at its highest point. I said zenith, but I meant its highest point, because it's not the zenith of the sky, it's just the highest point the sun gets on a given day. All right, and that's, you can see, right? This just simply isn't as hot, as the sun doesn't get that high. Now, if you're wondering about this lopsided figure eight, that has to do with mostly the elliptical shape of Earth's orbit, okay? In fact, it's not a perfect circle. So, in summary, the real reason for the seasons is Earth's axis points in the same direction to Polaris, right, to the background of distant stars, all year round. So its orientation relative to the sun changes, sometimes pointing away, sometimes pointing towards, sometimes pointing neither away nor towards, right, when it's pointing off to the side, right? And that would occur at the points in between the solstices, which are known as the equinoxes. In fact, I'll skip back to that real fast. These are the two equinox points. There you actually have a length of day that's shared by the entire planet. So on those two particular days of the year, because the axis is pointed away from the sun, as I said, neither towards nor away, at kind of a line that's tangent to the circle, the orbit of Earth around the sun. Well, on that day, the whole Earth has a 12-hour sunlight, 12-hour period of sunlight, and then 12 hours of darkness, because we're exactly lined up that way. That's why it's called equinox. It's equal. It's an equal day, okay? Summer occurs in your hemisphere when sunlight hits it more directly, right? As we saw in the picture, when the sun is directly overhead. Winter occurs when the sunlight is less direct. Okay, so axis tilt is the key to the seasons. Without it, we would not have seasons on Earth. Earth would still be sustainable for life, right? If we didn't have seasons, but they certainly had a dramatic effect and have driven evolution, you might even say. All right. So why doesn't the distance matter? Well, the variation of Earth, the Earth-Sun distance is small, as I said, right? It's actually about 3%. It's less than 10, but it's significantly less than even 5%. The small variation is overwhelmed by the effects of axial tilt. Okay, so it just doesn't show up. All right, even though when we are closer, we are getting significantly more intense sunlight, but that sunlight probably gets driven around by weather patterns, or the energy that gets imparted to the atmosphere gets driven around by weather patterns, and it just simply doesn't have, as I said, an effect of having, on average, hotter summers in the southern hemisphere. We just don't see it. The variation in any season of each hemisphere, well, it just is just natural, right? The sun distance is even smaller. Okay. So how do we mark the progression of the seasons? Well, we've talked about the four special points in the figure a few slides back, but we're going to summarize them here. We have northern summer, which happens in June, specifically at the June solstice, okay? That is the longest day of the year, all right? So that's not all of summer, but that marks the beginning of summer, the longest day of the year, okay? Then we have the December solstice, which is northern winter, and that is the shortest day of the year, okay? The shortest day of the year in the northern hemisphere, okay? Now, of course, the December solstice is the longest day of the year in the southern hemisphere, right? Because they're exactly opposite. Then we have the two equinox points. Here we don't have to separate in the opposites because everything's shared. On March, on the day of the equinox, which is around March 21st, the entire day has 12 hours of sunlight and 12 hours of darkness. Likewise, halfway between the solstices, but on the other side, we have the September equinox, okay, also called the fall equinox, and that equinox, again, is going to be 12 hours of sunlight and 12 hours of darkness for the whole world. Okay, so we can recognize solstices and equinoxes by the sun's path across the sky, all right? Well, this is going back to that figure we saw where we saw the relative points of the sun, but here we're showing them as, instead of, kind of snapshots that show that figure 8 pattern, which is beautiful, instead we're showing it as the arc of the sun on particular special days, particularly the solstice, the equinox, and the December solstice. So the summer solstice and the winter solstice, okay? So those 3 particular days. And this example is taken for a northern hemisphere case, okay? And it's taken where we're not at some extreme point. This is not someone at the equator. This is someone at some middle latitude in the northern hemisphere, okay? So we can see that in the northern summer, the June solstice, the sun has a long route through the sky, right? Because it's a long arc, and it gets high up in the sky, so it has a high angle above the horizon, right? This angle here. On the equinox, it's still a fairly long day, but it doesn't get as high, right? That would be this angle. And then the extreme case is the winter, where the sun has a much shorter path, so shorter day, and it doesn't get that high at all, okay? So those are examples of those 3 special days and how the path of the sun creates different weather, different amounts of heat getting, warming up the land and the air and the sea. All right. So the path of the sun in the summer solstice in the Arctic Circle is pretty cool because this is that idea of it never setting. This is what perpetual sunlight looks like. Okay. And on these points with the midnight sun, the day that doesn't end up above the Arctic Circle, the sun still goes up and down. It still varies in height. It just never sets below the horizon. Now, this isn't at some extreme point, just a few hundred miles away from the North Pole. This is more the inhabited part of the Arctic Circle. These are the few cities that are above the Arctic Circle, like in northern Canada, Alaska, northern Finland, or Norway, even Russia, right? There's some cities up there above the Arctic Circle. And those cases, they still have a couple days of the year at least where the sun never sets, but it will dip down near the horizon, but then just come right back up, right? So this would be around midnight here, where the sun gets to its lowest point in the local sky, but never sets. Okay, so we've got this axial tilt. We know it's relative to distant stars, particularly with its north pole pointing towards Polaris. But why do we have axial tilt? Well, axial tilt is like a spinning top. It's a type of motion, rotational motion, known as precession. And that means that our axial tilt, although the 23.5 degrees remains fairly constant, it does revolve relative to those distant stars. In other words, our current rotational axis will not always be pointing towards Polaris. Over thousands of years, it will point to totally different stars. Okay, so let's see what the time frame is of this precession. Okay, so although the axis seems fixed on the human time scale, right, so it's been pointing towards Polaris for hundreds of years, it actually precesses over a period of 26,000 years. So that means that wherever the north pole of our planet is currently pointing relative to distant stars, in 26,000 years, it will come back to be pointing there. But in the meantime, after half of 26,000 years, so 13,000 years, it'll be pointing in a totally different direction, right? It'll be pointing about 40 degrees the other way because it's going to be tilted all the way that way, which is, so I'm saying, it'd be 23 and a half times 2, so I guess that'd be 47 degrees all the way to a different part of the sky, essentially a different part of the Milky Way galaxy, okay? So currently, we're pointing at Polaris. In 13,000 years, we'll be pointing at Vega. Vega will be the North Star, very different type of sky, okay? So that period, right, of completing, a very different North Star over 13,000 years means that it has varied over recorded human history. If we think about ancient Greeks and their observations of constellations that were done 4,000 years ago, well, in 4,000 years, we have actually had a significant change, because you think of 4,000 being about a third of 13, that means there's been about that much change, that much of a precession, okay? So a significant, about a sixth of the overall precession since recorded, sky observations. That means the constellations have certainly changed, and scholars will compare the descriptions of constellations by ancient Greeks and other ancient peoples, and they'll notice those differences, and they're able to track what they'd expect from the precession. But we know the precession, independent of those observations, they just support what scientists already notice, because we can measure its tiny changes over shorter periods of time, like a human lifetime, even though they are functionally imperceptible, right? At least for everyday life. Okay, so the positions of the equinoxes shift around the orbit. So the spring equinox, once in Aries, is now in Pisces. Okay, and this is certainly the sort of thing that was recorded by early peoples. All right, so that's the precession, just like a spinning top. Spinning tops have precessions that are probably, a fraction of a second, right, for a normal toy spinning top. But here we have a much larger object, a lot more mass, so we have a much more elongated precession, 26,000 years. But it's the same physics. Okay, so in summary, what have we learned in this section? We've learned that the tilt of Earth's axis causes sunlight to hit different parts of the Earth more directly during the summer and less directly during the winter. Okay, but what summer and winter are we talking about? Well, those terms, like if you're in Australia, you refer to December as the summer. Of course you would, right? It would just come naturally. You're like, hey, what are you doing in December? It just happened. What are you doing the December? It's a combination of December and summer. But regardless, that's when we refer to summer, it's the warmer time of the year. Okay, we just have opposite summers in the north and south. We can specify the positions of an object in the local sky by its altitude above the horizon and its direction along the horizon. Okay, well, why are we pointing this out? Because we've said this before. Well, that's so important for the sun, right? The sun's highest point in the sky on particular days of the year. The summer and winter solstices are when the northern hemisphere gets its most and least direct sunlight, respectively. Okay? The spring and fall equinoxes are when both hemispheres get equally direct sunlight. How does the orientation of Earth's axis change with time? That's the precession. The tilt remains at about 23 and a half degrees, okay? But it does actually vary. It varies by a couple degrees, which is so fascinating. But more interestingly, more directly, it does create a complete rotation in 26,000 years, a precession, all right? So that's a lot of rotational motions, right? We have orbit that takes 365 days. We have a rotation that takes 24 hours, and then we have a precession that takes 26,000 years, okay? And there's more movement than that. There's, of course, the fact that the sun is orbiting around the galaxy, which takes about 150,000 years, so there's all kinds of different motions all stacked on top of each other. Okay, now, speaking of motions and periods of motion, let's talk about the moon, okay? We have a very dramatic, amazing moon. In later chapters, we'll talk about theories about how the moon was formed, but it's very fascinating. It's quite large. It causes very dramatic tides, and it's beautiful, okay? So what are our goals for learning about the moon, our constant companion? Well, we want to answer, why do we see phases of the moon, okay? So simply put, and what causes eclipses? And also, squeezed in there somewhere, we'll talk about why we always see one face of the moon. Okay, but first, why do we see phases? Okay, well, the phases are because of the moon's relative position. Okay, so in a fairly well-scaled image here, we have Earth as a small blue dot, okay? We then have the orbit of the moon around Earth, with its closest point at 356,000 kilometers and its furthest point at 407,000 kilometers, okay? Now, it's fairly circular, but it's not perfectly circular. It's elliptical, okay? And so that means that the Earth is at one of the foci of the ellipse, okay? But still, not a lot of variation, just like Earth's orbit is fairly circular, but does have some variation. Here is the moon, essentially to scale, shown as just a small black dot, okay? So this is kind of cool because this is a scale image, because the moon is actually quite close. The moon is only 60 Earth radii away from Earth, okay? That's unusual for such large moons, as far as we can tell, certainly within our own solar system, and just based on how moons naturally form. So we're lucky to have such a big moon, okay? And Earth, this is at a 1/10 billionth of its actual size, and this is the moon, also at that same 1/10 billionth of its actual size, okay? Now the sun, at this scale, will be really far away. It'd be 15 meters away, right? So we got, have this small piece of paper, and somewhere 15 meters away is going to be the sun. And if you're looking at this on a screen that isn't showing it as kind of typical paper size, then of course the scale will be slightly different. But some many meters away is the sun. The sun also at this scale is going to be, let's see, because it has a radius that is over 1 million miles. So the sun is bigger in size than the orbit of the moon around Earth, right? It would dwarf Earth because obviously, it's bigger than the whole orbit of the moon. Right? It would take up a huge amount of space over here, again, some 15 meters away. Okay, well, the orientation here is what creates phases. Consider this phase shown right here, where we're looking at a point, right? We're looking into a view, right? Imagine you're some spacecraft over here. This is an actual image taken by a spacecraft. And that spacecraft is looking off to the side. So the view is in this direction, as shown by that large blue arrow. Well, if you're looking in that direction, you would see the moon half illuminated by sunlight. And the moon would be over here on this side, in this case, right? If we're imagining looking exactly this way, spacecraft. All right. I wrote spacecraft. There's an F there, of course. Okay. Well, or anyway, so we have the moon over here. It's half illuminated because this is the side over here. The illuminated side is the side that's being hit by sunlight and reflecting that sunlight, and that reflected light is what we're seeing. This darker side over here, we don't see any sunlight because that's facing away from the sun. And since we're looking from the side, we're only seeing the illuminated side. Simultaneously, in this case, we don't often have this view. We also see Earth from some great distance, and Earth we see is in a phase because it has one half of it also illuminated and reflecting sunlight, and then the dark side, since there's no light hitting it, it just appears dark to us, okay? And now, of course, that means that the half of the world that appears dark would be in nighttime for anyone on the surface of the Earth, okay? So the Earth has phases too if you watch it from the moon, for example, or you watch it from somewhere else in space. But we don't do that. Instead, we look up at the moon and we see the moon's phases as the moon is positioned differently towards the sun. All right, but let's get more into it. So here are all the phases in order. And you can imagine the phases by standing in front of a lamp and thinking about the light that's hitting the ball that represents the moon and getting reflected off the surface of that ball. Because if you hold a ball or sphere in front of you and there's a light source over here, well, you're not going to see the bright side of the moon at all, or the ball. You're only going to see the dark side. So you would just see a faint silhouette of light because the bright side is facing away from you. Well, that corresponds to a new moon, a moon that you can't really see, okay? Also, a moon like that, from the perspective of a rotating Earth, that it makes everything appear to rise in the east and set in the west, would rise and set with the sun. So even with it having a faint silhouette around its edge, it's going to be completely washed out by the sunlight that it's moving near and with, all right? They're not going to track the exact same way through the sky, but they'll both rise and set at about the same time. Okay, now continuing with the phases, after the new moon, we have what's called a waxing crescent. Waxing means that it's growing. Crescent means that it's a small amount of reflected part of the moon. Now the moon has a little bit that you can see out of the corner of your eye, essentially. Now, a few days later, we have the first quarter moon. Okay, now the first quarter moon is when you're looking at a moon and you're seeing 1/4 of it illuminated. Because you're looking at one half of the moon, the half that would be facing towards this person's head, The other half that's facing towards us that we can see over here, they would not be able to see. Now, the moon always has one half illuminated, but the view would allow them to see 1/4 of the surface. Okay? Now, that name first quarter also means that it's 1/4 of a complete cycle, because we started over here at the new moon, now we're at first quarter, and we're 1/4 of all the way through the cycle. A cycle that takes about 27 Earth days. Continuing with the cycle, we have a waxing gibbous. Waxing again means that it's growing. Gibbous is given to the term between quarter and full. Okay? Now, when we get to the full moon, we're still only seeing half the moon because there's a half facing away from us. But if the person was to turn their head around and look, they would see the fully illuminated side. They're seeing all of the moon that is reflecting sunlight. That's why we call it the full moon. Okay? We're seeing a full sphere, or at least a full circle. We continue on, and now we're in the waning phases. Waning gibbous, waning means shrinking. Third quarter, we're 3/4 of the way through the cycle, and we're also seeing 1/4 of the surface of the moon. Then we have our waning crescent, getting all the way back to the new moon, completing the cycle. There's other information below each image that mentions when the moon rises, when it's at its highest point in the sky, and when it sets. And it's like you'd expect, with the moon rising and setting with the sun in the case of the new moon, rising at sunset and setting at midnight for the full moon, and everything in between for the other phases. Okay? So in summary, we have the new crescent, first quarter, and gibbous phases, which are all waxing when the moon is visible in the afternoon and the evenings, and it gets fuller each subsequent day. Then we have the phases full, gibbous, third quarter, and crescent, where the moon is shrinking or waning, and the moon is visible in the late night or morning, and it gets less full with each day and sets later. So, thought question 8. It's 9 a.m. You look up in the sky and see a moon with half its face bright and half dark. What phase is it? Okay, the time of the day is going to allow you to distinguish between it being a first quarter or a first quarter or a third quarter. Because otherwise, the fact that half of it is dark and half's bright, it could be either one, right? Because that description meets both of these criteria, first quarter and third quarter. But which one is it based on the fact that it's 9 a.m.? Third quarter, right? Because the first quarter is not up at 9 a.m. All right, so you can confirm that by thinking about the phases, thinking about the relative time that the moon rises to the sun. So here's the other really interesting thing about the moon. Okay, so far we've got the phases. Hopefully you can understand just the position of the sun relative, to the position of the moon relative to the sun, and all this motion, by the way, this motion of the moon, it's on the scale of 27 days to complete the full cycle. So that means that the moon is essentially motionless over any given night, right? There's very little of the phase that changes over one night because it's just 1/27th of the overall cycle. There's a little bit of change, okay, and people can finally notice it, right? Some people might say, someone might say, oh, it's a full moon tonight, and an astronomy student would say, well, actually, the full moon's at 3 a.m. Because yes, the moon is up all night on the case of a full moon, but it'll get slightly larger over the duration of the night, but only slightly, okay? So that's why we consider each day to just be one fixed phase. Now, second interesting thing about the moon, the fact that it has a synchronous orbit, okay? So it has synchronous rotation. The moon rotates exactly once with each orbit. Okay, so I said it has a synchronous orbit, but that just means that the orbit and the rotation are synchronized. This is very different from Earth, right? We spin on our own axis every 24 hours, but we complete an orbit in 365 days, or 365 times longer than our rotation, right? So there's a big difference between our orbital period, the length of an orbit, and the length of a day, the length of a rotation. Not so for the moon. The moon has a moon day, which is a rotation around its own axis, and an orbit around Earth that are about the same. So the orbit of the moon is about the same as the rotation of the moon. So the moon is rotating really slowly. Okay? Now this effect is called tidal locking because it's actually the forces between Earth's ocean that slows down both Earth and the moon that leads to this phenomenon. Okay, and the moon will remain tidally locked, but both Earth and the moon will continue to slow down, which means Earth's days are getting very gradually longer over the scale of millions of years, and the moon is drifting further and further away. Okay, but again, over the scale of millions of years. But currently, and for eons to come, the moon is going to be always facing us with the same side because of this equal period of orbit and rotation. And you can visualize this because if you think of someone spinning and they're facing some center column with a sphere on top representing the Earth, if they rotate, if they shuffle around their feet while also walking to the side at the same rate, so that the time it takes to complete a rotation is the same as the time it takes to complete an orbit, then they'll always face the sphere. All right? Interesting, right? That's what the moon has. That's a synchronous orbit. There are other cases of synchronous orbits in the solar system. Okay? So, how long would each day and night last if you lived on the moon? Think about how the moon faces towards the sun sometimes, and sometimes it faces away from the sun. And think about the length of an orbit, about a month. Okay? 1 month. Exactly, right? So the moon has a day that's 1 month long because the term month refers to the phases of a moon, or the moon. Okay, so what about eclipses? Because we have phases, right? And sometimes we've outright said that sometimes the moon is between us and the sun, right? Right here. This is a case where the moon is between us and the sun. Well, does that mean that every time the moon is between us and the sun, we have an eclipse? Because the eclipse is all about the sun being blocked by the moon, at least a solar eclipse is. But if that's the case, it seems like they'd be a lot more common. They seem to only happen every decade or so, right? Well, that's because it's not every time. We have to have very specific conditions for the moon to exactly block the sun. Okay, well, let's break down some of the understanding and the terminology of an eclipse before we describe those very specific conditions. Okay, so the sun is very far away, right? But also very large. The moon is rather relatively close and much smaller than the sun. That means that both of them have the same angular size. They both take up the same amount of space in the sky. And we talked about this in the last video. Now, both of them cast shadows. Those shadows have two parts called the full shadow, or the umbra, and the partial shadow, or the penumbra. You've probably noticed partial shadows and full shadows if you've ever walked around with a flashlight. Okay, so there are, in addition to the very dramatic solar eclipses, much more common lunar eclipses. Lunar eclipses are caused when the moon is an Earth shadow. Solar eclipses are caused when the sun is blocked by the moon. So in other words, we're seeing the moon shadow on the surface of Earth. Okay? Now, the reason that one is much more common than the other is because about half the Earth is able to see the moon when it passes through Earth's shadow. Only a tiny portion of the Earth is able to see the shadow cast by the moon when the moon is between us and the sun, which you can actually see in this figure because the penumbra, the full shadow created by the moon, is just creating a small little dot on the surface. Okay, it creates essentially a large dark region, which is called the region of totality, or the path of totality, because that big dark spot travels across the land at a rate of 1 kilometer per second, which is also the speed of the moon relative to the center of the Earth, because its shadow moves at its same speed. And so that big dark shadow is about 100 kilometers across. It varies depending exactly where in the elliptical orbit the moon is. That's coinciding with the eclipse, but it's some 100 or so kilometers across, this big dark shadow racing across the surface of the Earth. And if you happen to be in its path, then you see a total solar eclipse. But notice there's also the penumbra outside of the umbra, and anyone in this part experiences a partial solar eclipse because they'll see the sun get half covered. Also really interesting, the day gets noticeably darker, shadows change their shape, but it's just not as dramatic. All right, so here's an example of a lunar eclipse. This is just a normal moon that's not an Earth shadow, and then we can see it passing into Earth's shadow, getting darker and darker until it's completely in there, because when it's mostly in Earth's shadow, the bright part is all we see because our eyes adjust to the light. But once the moon is completely in Earth's shadow, then it's picking up much fainter light from the ring of sunsets around the entire planet Earth, that light still getting reflected off the moon's surface, and that dimmer, redder light we see, and then we have that lunar eclipse, that blood moon as they are called. Okay, so lunar eclipses can occur only at full moons because they have to occur when the moon is on the other side of Earth from the sun. Okay, we can also have partial lunar eclipses where the moon goes partially into Earth's umbra, but is also sticking out into Earth's penumbra. Okay, furthermore, we have cases where we have the moon only go through the penumbra, and it's just completely partial, all right? In this case, it's really just kind of a fainter moon. It's the least dramatic of all the eclipses, okay? Solar eclipses, if you are inside the path of totality, if you're inside of that shadow that the moon casts on the surface of Earth, would look something like this leading up to it, where the sun is getting progressively more covered up to the point where it gets completely covered, all right? Totality, that moment of being somewhere on Earth and looking up and being in the shadow of the moon and the moon being exactly in front of the sun only lasts a few minutes. It's going to last somewhere from 2 to 6 minutes, because after that, the alignment won't be perfect for your position on Earth. It will have moved somewhere else, and, well, then it will start to get uncovered and it will go back to looking like a partial solar eclipse that the rest of the world only ever saw. Furthermore, you could keep up with a solar eclipse if you could fly at 1 kilometer per second, or 1,000 meters per second. You can keep up with the solar eclipse and actually stay in the path of totality. That does mean maintaining Mach 3. It has actually been done a few times by very fast military aircraft, but eventually they run out of fuel. Okay, so solar eclipses can occur only at new moons. Why? Because the moon needs to be between Earth and the sun. All right, the moon needs to be between Earth and the sun. Now, there are 3 types of solar eclipses. There is a total solar eclipse that one path of people can see on the Earth as the shadow moves across some path. There's the partial solar eclipse that's seen leading up to a total solar eclipse for some people, and then seen by a much larger region of all those in the penumbra. Furthermore, there's an annular eclipse, which it requires the same exact conditions of being in the path of totality, but occurs under another level of conditions where the moon happens to be at its furthest point, where it's some 406,000 kilometers from Earth, thus giving it a smaller angular size, because when things are further away, they appear smaller, and thus the moon looks smaller, and it doesn't completely block out the sun. Right, because it's further away, it's not taking as much space, and it's actually letting some of the surface of the sun, known as the chromosphere, be visible. And so instead, we have a ring of fire, or an annular eclipse, and we don't see the corona at all, because the ring is so bright that it washes out the light. Because in the total solar eclipse, the eerie white gas around the sun is the corona, which is otherwise invisible. Okay. Oh, and this is that idea of the shadow of the moon on Earth. This is anyone in this area is going to see the total solar eclipse, or an annular solar eclipse if the conditions are just right. And then this shadow races across the surface of the Earth, right, until it leaves, and then the whole event is done, taking some 12 hours or so, and it's moving at a rate of 1 kilometer per second. Okay, so why do solar eclipses only occur sometimes? Why do lunar eclipses only occur sometimes? It's because the moon's orbit is tilted relative to the ecliptic plane. So this is another tilt. Obviously, these tilts are a big deal in astronomy. We talked about the axial tilt of Earth's rotation, that 23.5 degrees, which creates seasons, a very dramatic effect. Well, the moon's orbital tilt is smaller than 23.5 degrees, but it means that we don't always have the right condition for eclipses. In other words, the sun and the moon aren't always lined up. Okay, so here's the tilt. Let's see if we can find the value. 5-degree tilt. Okay, the tilt, just like Earth's axial tilt, remains fixed to distant stars, not fixed relative to the sun, which means sometimes the tilt is pointing up towards the sun. So the orbit we can see is pointed up towards in the direction of the sun. Other times it is pointed up away from the sun, right? 6 months later, in fact. Okay, now, in this picture, you might have noticed that for some reason, space is represented by the surface of water. Well, that's actually just an analogy, just to show just the right points when we can get a solar eclipse. Because the solar eclipses can only occur when we have that tilt lining up with the direction to the sun. All right. So if there happens to be a new moon, when the tilt of the moon is lined up in such a way that the moon is passing through the ecliptic plane, shown here as splashing down into the surface of water, that's going to be the right conditions for a solar eclipse. Likewise, when there's a full moon near this node, then you can have a lunar eclipse. okay? These are called eclipse seasons, and the crossing of the ecliptic plane and the orbital plane of the moon, those are called nodes, okay? So that means you have to have just the right conditions. They don't happen every month, right? Because otherwise there would be 12 potential solar eclipses or lunar eclipses per year. Instead, they happen how often, right? Well, we can see they only happen twice a year. So there's one chance for a lunar eclipse over here, and then there's going to be one chance for a solar eclipse over here. You might think, well, but aren't there other points where aren't there other nodes? Well, this node here can't lead to a solar eclipse nor a lunar eclipse because the moon is in a first quarter phase. Likewise, when it's in a third quarter phase. So these ones are not valid cases for an eclipse, okay? So you just have 2 times per year, this one, so these 2, that are potential eclipses, all right, if all the other conditions are met. So, in summary, it must be a full moon for a lunar eclipse or a new moon for a solar eclipse. And, because that's not enough, the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane, points known as nodes, right? All right, so people will track this. They'll take into account the fact the elliptical orbits of Earth and the Moon. They'll take into account all these slight variations, okay? And they'll come up with predictions of when eclipses will occur, which are very, very accurate. So eclipses reoccur with an 18-year cycle, all right? Which also more accurately is 11 and 1/3 days. So 18, 11 and 1/3 days, 18 years, 11 1/3 days. This cycle is known as the Saros cycle, all right? And it's going to lead to different types, partial, total, even annular eclipses in rare cases, and the location varies, okay? So sometimes we have paths of totality that are way down in Antarctica. Other times we have paths of totality that cross right across North America. We had one that crossed back in 2017, this big red line cutting across the country, right? And we're going to have another one in 2024 that'll come up through Texas and cross across the country as well. And then finally another in 2042. All right, so pretty interesting stuff. And if you travel somewhere else in the world, you can see there's other ones coming up even as soon as 2023 if you travel to, say, Papua New Guinea. All right, and that one also goes through Eastern Australia. Okay, and those are the paths of totality. Notice the paths of totality also vary in thickness, and that's just due to how close the moon is to or away from the Earth. So in summary, what have we learned? We've learned, why do we see phases of the moon? Well, we learned that the half moon is lit by half the moon always is lit by the sun. Half of it is always in shadow. Okay, and its appearance to us is determined by the relative position of the sun, moon, and the Earth, whether we're seeing that illuminated half or not, because it might be facing away from us in the case of a new moon, when the moon rises and sets with the sun. We've also learned quite a bit about eclipses. We've learned that lunar eclipses are when Earth's shadow is on the moon. We've learned that solar eclipses is when the moon's shadow is on the Earth. We've learned that the tilt of the moon's orbit means that eclipses occur during 2 periods of each year, the eclipse seasons. All right, so let's go into our final section here, the ancient mystery of the planets, and really talking about apparent retrograde motion, this idea that planets over many nights appear to drift backwards in the sky or drift towards the east. So why was planetary motion so hard to explain in the past? That would be, hundreds of years ago, before the Copernican revolution. And why did the ancient Greeks reject the real explanation for planetary motion? Okay, so here are the planets. They all are on the ecliptic plane, so they kind of look like you can connect the dots and have one arc across the sky. They vary in brightness, and ones you can see with the naked eye. These are all the ones that you can actually see with the naked eye: Jupiter, Saturn, Mars, Venus, and Mercury. This is a dramatic case of where all 4 of them are visible, or all 5 of the naked eye observation planets are visible. This would only be true very early in the morning. Sometimes right after sunset as well. And that's because Mercury, which is quite bright, is almost always between us and the sun because it has a small orbit tightly around the sun. So it's hard to see when it's not daytime, right? And when it's not washed out by the sunlight. So you have to catch it just the right time, right before sunrise, for example, which I think is when this photo was taken. Okay? So planets usually move slightly eastward from night to night, okay, relative to the stars. So they keep moving towards the east. That's their standard motion. I think I just said that a minute ago that they normally drift towards the west, but no, they normally drift towards the east due to our counterclockwise orbit, okay? But sometimes they go westward, right? They actually change their direction relative to the fixed stars, okay? This apparent retrograde motion has always fascinated people that observe the night sky. Here's an example, right? So we have the drift moving. So let's find our earliest date here. Yes, so we're going to start here with 2011, and we have Mars, yes, Mars moving in its normal direction towards the east over each night. It's going kind of east and towards the horizon, but with a general east direction, all the way up to July of 2012. But then we're going to have it start to drift the other way. So let's find. Okay, sorry. Okay. So we have July. Oh, that's the very end. So this is the last date. So it's in fact it's going to go eastward up to this point. So the direction is this way. All right, so it's continuing eastward. Here's the turnaround point. So on the 23rd of January in 2012, so some few weeks after November, then we're going to have it reaches as far eastward as it's going to go before it retrogrades. Then it goes with apparent westward motion up until April, and then returns to its normal eastward track all the way up to the July of that year. All right, and it'll take a while until it does that again. But every 2 years, it will do a little loop-de-loop as it appears to move back towards the west. Why is this? Well, that's because we're lapping Mars. And as we look towards Mars relative to the distant backdrop of unmoving stars, it's going to have different positions relative to those stars due to parallax, due to the fact that we're moving relative to each other and Mars is relatively close to us. So it's easy for us to explain because it occurs when we lap another planet, okay? Or in the case of Mercury or Venus, when they lap us. But it's very difficult to explain if you think that Earth is the center of the universe, okay? If everything orbits Earth, then there's really almost no explanation for this. In fact, ancients considered but rejected the correct explanation because they thought if that was true, if Earth was orbiting and the orbit had to be as big as their calculations suggested, which may have been close to the current known value of 150 million kilometers, well, that meant that we're moving through a huge amount of space, which is first a jarring idea. And shouldn't then the stars also move relative to each other? Well, what they never thought of is how far away the stars are. The stars are such vast distances away that there's no observable parallax of them relative to each other. Whereas the planets are close, so we do see the parallax of the planets. Okay? So here's the idea. This is lapping someone in the literal sense of a racetrack and how that person would appear to be oriented differently relative to the wall in the background, the brick wall. And the same idea as Earth laps Mars, Mars appears to be at different points relative to the backdrop of constellations. All right. So the reason that those ancient scientists, those ancient Greeks, the ancient Egyptians rejected the idea of Earth's motion around the sun, rejected the idea of the sun being the center of our solar system and the known universe, was because of the inability for them to observe stellar parallax. Because they thought that there must be some stars that are close enough that as we move through our vast orbit, that star would appear to move relative to the backdrop in the same way that Mars does. But we don't see that. There is no way to see that unless you use a telescope. The largest amount of parallax that occurs is about 1 arc second. That's the closest star to us, Alpha Centauri or Alpha Proxima. It's actually a 3-star system. But any one of those nearby stars, when we move relative to them, and then them being so much closer than many other stars, they do drift back and forth. They shift back and forth as we essentially not lap them, but as we move with different angles of view towards that nearby star. But that angle difference is just 1 arc second, a tiny amount, and something you can never measure with naked eye observations. All right, so the Greeks knew that the lack of observable parallax could mean one of two things. Stars are so far away that stellar parallax is too small to notice with the naked eye. That's the real reason. Okay, or that Earth does not orbit the sun. It must be the center of the universe. Okay, with rare exceptions, such as Aristarchus, the Greeks rejected the correct explanation, right? They just couldn't imagine it, right? It was a lack of imagination because they did not think that stars could be that far away. And it reconciled other concerns about understanding the physics of inertia and how could we be on a planet moving that fast and not notice it, right? So thus the stage was set for the long historical showdown between Earth-centered and sun-centered systems leading up to the Copernican revolution. So in summary, what have we learned? Well, we learned what was so mysterious about planetary motion in our sky, Like the sun and the moon, planets usually drift eastward relative to the stars from night to night, but sometimes, for a few weeks of the year, they appear to go the other way, okay, as we lap them. And why did the ancient Greeks reject the real answer? Well, that's because most Greeks concluded that Earth must be stationary because they thought the stars could not be so far away as to make parallax undetectable. But they were wrong. All right, so this concludes our second video for this lecture. I hope it has been interesting and informative. Thank you so much for watching.